All right, in this video, we're going to look at where functions are increasing, decreasing, max and mins. That's going to be pretty easy. And then we're going to look at symmetry, which is where is a function symmetric. And that's going to be pretty easy if you're looking at a graph, but a little more involved if we got to do it algebraically. All right, so let's start with a basic application. I got a hiker hiking a long hike. So we got he's 8 hours. He goes up a mountain, comes down, goes up, and just levels off on a ridge. So let's finish this x-axis. Long hike, 14 hours, and then we'll just say he stops at 14 hours. Let's cut it off there. So I want to know for which intervals is the function increasing or decreasing, or in this application, for which intervals is the function or the altitude increasing, decreasing, because that's the application. So you can notice I don't have any values on the y-axis, and I did that on purpose. So let me show you the first interval of increasing, and then let me explain it. He's increasing on between 0 and 6 hours. Okay, and then let's say I did have numbers here. Let's say that's, I don't know, 50, and he hikes up to 1,000 feet. Big climb. You wouldn't say he's increasing from 50 to 1,000. I mean, that makes sense. That's the y value, but the question for increasing, decreasing is always for which x values, or in this case, t, is the output altitude increasing. Okay, so our answers are always values for these questions, always values for the input variable, right? Which is a little confusing. And then he's going to increase from 10 to 12, right? We're not interested in what the increase is. It's just for which inputs is the output increasing. And then it looks like we're decreasing from 6 to 10. And then you can see he's constant here from 12 to 14. So that's where he is not increasing. The altitude is not changing. It's constant, right? It's just leveling off here. And that's from 12 to 14. Okay, so that's a pretty basic application. I mean, you're just looking at the graph. Here's another one. If we had to answer this, well, what would you say? Well, I'm going to say, let's just do the increasings. No, let's do the increasing. And then we'll take a look at the decreasing. So where is it increasing? It's increasing from, as you go from left to right, remember, just x values. Negative infinity up to when? Be careful, you're going to want to say 0. That's the y value here. But it goes from negative infinity to negative 1. These have to all be at x values, right? Y goes from negative infinity to 0, up and down. But x, left to right, negative infinity to negative 1. Then it decreases, then it increases again. Let's just list them. From x equals 0 to x equals, looks like it's about right there, and then it goes constant from that interval. So we'll go from 0 to 1.5, we'll call it. Increases again from 2.5 to, let's call that 3.75. Does that make sense? It's going to, whatever x value that is when it starts decreasing. And then it would decrease from there all the way down to infinity, negative to infinity. Sorry, let me clear that up. So let's do decreasing. It decreases from negative 1 to 0, x values, constant there, and then 3.75 to positive infinity. Little tricky, but that's the x values. As x goes from here on forever, y goes down. Okay, let's see how we did with my estimates, because I got the answers here. Oh, they're just doing the halves, 3.5. So we call that 3.5. Okay, and then constant is 1.5 to 2.5. Okay, so here's like a outline of how we would do these, but for the most part, these are your mathematical technical definitions. We don't need these. I included them because that's should be included in a good set of a textbook or guided notes. But you just say, I look at the graph, when's it increasing, decreasing? We don't have to worry about, oh, if the next output is greater than the previous output, then I know it's got to be increasing. So don't worry too much about those definitions. We don't want to make it more complicated than it is. Okay, same thing with this one, only we introduce a new topic here, max and mins, which is also really easy. I'm not going to worry too much about the definitions. Just look at your graph and say, oh, that's a minimum value. Okay, and we call it relative min because there are smaller values there. But in a certain interval, it's the smallest value, right? It's just a peak, right? If it peaks or if it bottoms out, then we call it a relative or a local. These are the same thing. Relative and local, same thing. So the local minimum is the y value, and it happens when x is 2. The local max is the y value, and it happens when x is negative 2. Pretty straightforward. Moving on. All right, by mathematical definition, it changes. We can connect this to increasing, decreasing. This should make sense. When it changes from increasing to decreasing, it's a maximum. If it were to change from decreasing to increasing, that's going to be a minimum. All right, let's talk about symmetry. Here you have a symmetric heart, right? If I draw a line right through it, it's symmetric. If that was the y-axis, this is symmetric about the y-axis. If you held a mirror right here, it would reflect itself over the y-axis. This is symmetric around the x-axis. If I held a mirror on the x-axis, it would reflect itself. Okay, now, mathematical definition. A graph is considered symmetric to the x-axis. If A and B is a point, so what would that reflected point have to be? Well, it has the same x value, but the negative y value. There's our mathematical definition. So if AB is on the graph and a negative B is on the graph, it is going to be symmetric around the x-axis. Same idea here. All right, this is symmetric around y. How do I do this mathematically? Well, if negative AB is on my graph, then if I reflect that over here, what's that point? It's the same height, but the x value would be positive. Okay, and we're going to use these concepts when we do this algebraically. Here's an interesting one. This one is symmetric around the origin. This one's harder to see. The idea here, let's see if I can do this. If I rotate this 180 degrees, I get the same picture. Let's see. Rotate 180 degrees, same picture. Okay, so that's the way you can try and view it on the graph. Is it symmetric about the origin? Well, if I can do this, you'd have to kind of do that in your head, and I get the same image. It's symmetric around the origin. Mathematically, if AB is on the graph, how do I reflect through the origin? You take the negative of both. Not quite as simple as symmetric around x and y, but that's the concept here. That's the definition of symmetric around the origin. Okay, so mathematically, think about that, if that makes sense. If we replace every x and y with a negative x and y, you get the same equation. All right. Let's talk about this. Let me try and clear that up. If I replace every x with a negative x and I get the same equation, then it's symmetric around the y-axis. What does that mean? Well, let's go back up here. This one's symmetric around the y-axis. How does that make sense if I replace every x with a negative x? Well, the idea here is if I plug in, if this is the point, let's call it 2, 4, right? And if I plugged in negative 2, I get the same output. Okay, so the connection here is what happens with a positive and a negative x, same output. All right, so let's do a couple of these. They're a little tricky. Determine if the graphs are symmetric with x-axis, y-axis, and the origin. By the way, we're going to get to this next. If it's symmetric around the y-axis, we're going to call it an even function. If it's symmetric about the origin, we're going to call it an odd function. And we got nothing for symmetry around the x-axis. Okay. All right. Let's take a look. So how do I do this? Well, the idea here is if I use my function notation, just investigate f of negative x. This, I think, is the best way to do it, and see what happens. This is a little tricky. If I get the same function here, right, as this, then it's symmetric around the y-axis. That's as if you input a negative and or the positive and you get the same output, then it's symmetric around the y-axis. All right, so you got to do some algebra tricks here. Negative x quantity squared is the same as x squared. Right? If I square a negative value, it's the same as squaring the positive. Same thing with the fourth degree, any even power. That's why we get this name even. So think about it. Negative 6 times x to the fourth is the same thing as negative 6 times negative x to the fourth. Anything you plug into this is going to be a positive x to the fourth. Plus 2. So look at what we just did. Same thing. If I plug in negative x, and I get the same thing as if I were to plug in positive x, then that is symmetric around the y-axis, which is also the same thing as calling it an even function. You kind of get the idea why it's even, right? Because it's not always going to be the case, but there's a hint. If these are even powers, then there's a chance that it'll be an even function. All right, let's look at an odd one. Well, my guess is this is odd, but let's take a look. F of negative x. This one's a little more complicated. Let's give myself a little more room here. F of negative x. So that is same idea. Plug in negative x anywhere you see an x. Remember, I started these the same way, and then I'm just looking at what I get as a result. So if I cube a negative x, that's negative x times negative x times negative x. So there's 3 x's, which gives me x cubed, but a negative times a negative times a negative is going to be a positive. I'm sorry, a negative times a negative is going to be a positive, and then times another negative is going to be a negative. Okay, so I end up with negative x cubed. Negative x quantity cubed is the same thing as just negative x cubed. So I'll put that out front. Same thing happens with this because it's an odd power. So a negative x quantity cubed is negative x to the fifth times a negative gives you a positive x to the fifth. Okay, let's look at what happened here. My original function was 2x cubed minus x to the fifth. When I plug in negative x, I get the opposite of that. We can see it. Oh, I forgot my 2. We can see it if I factor out a negative. And then there's my original function. So think about this. I plug in negative x and I get the opposite, the negative of my original function, right? My original y or f of x. And that has to do with if I plug in the negative value, I get the opposite sign. So think about that. Here's at the point AB. What I ended up doing with that algebraically, I plugged in a negative input. And what was the result? I got the opposite of the original function, the negative of the original output. And that's going to indicate that it's symmetric around the origin, which means it's an odd.